Hello everybody. We're going to do a little ICP review here for our last couple weeks we've been talking about. The last couple weeks we've been talking about three different topics, or overarching topics. We've been talking about light, color, and we've talked about electricity. When we think of light, we need to be thinking about, is light a wave or is it a particle? For color, we're going to be taking a look at primary colors and combinations. For electricity, we're going to be thinking about circuits, voltage, current, and resistance. Let's first take a look at light. The first thing we need to think about when we think of light is it a wave or a particle? Now, this was a long debated topic out the science community all through the early centuries, like starting in the 1600s all the way up to the mid-1900s. And it's very disputed. A lot of different scientists had different opinions. Some scientists who thought it were waves, sometimes scientists thought it was waves, and other scientists thought it was a particle. Some of the scientists that thought it was a wave were René Descartes and de Broglie. René Descartes thought light moved through a medium called ether that populated the planet, and so it moved through like a wave. De Broglie said that everything that can move or has momentum has a wavelength. So both of these people thought that light was a wave. On the other side of things, scientists like Einstein thought that light was a particle. Einstein thought that light consisted of small pieces instead of a continuous spectrum, and he called those small pieces photons. This led to the idea of the photoelectric effect. The photoelectric effect is the idea that, and it's experimentally proven, that if you shine a right kind of light on a metal, it releases an electric charge and can create a current. So Einstein's photons supported the photoelectric effect. All these different views clash together, but however, Young's double slit experiment put them all to shame. Young was the name of a scientist in the, I believe, the late 1800s or late 1900s, so right before the turn of the century. And Young's double slit experiment looked something like this. What Young did was he took a light source right here, a light source, and what he did was he shot one photon at this double slit. So ideally, if he shot one photon at the slit, it should just follow a path, pick a hole, and hit the screen. And guess what? That's what it did. Photons came through, they went and hit the screen. But they started going through both of them, and then some started going all the way out here, and others all the way out here. And he started to get this distribution. This distribution here represents the number of photons, or the amount of light you could see on the screen at different intervals. The distance from the screen indicates the intensity. So at this point here in the middle, it would be really, really bright and very visible. Out here, it would not be as visible. Also, in the dips, Young noticed that there was a dark spot. You couldn't see anything. What this is called a diffraction pattern. A diffraction pattern is something that a wave does. But Young was shooting particles. He wasn't shooting waves. So this led to the idea that light is both a wave and a particle. Because light is a wave, we can think of it as a bunch, we can consider different types of light waves. And this all comes off the idea that the speed of a wave s is equal to lambda times frequency. And it was experimentally measured that the speed of light is equal to a constant c, which is then equal to 300 million meters per second. That's really fast. Okay, really, really, really fast. Nothing on Earth that we know of can get to that speed except for light. Okay, but because it's constant, we can determine the frequency of all these others if we just know the wavelength. So, the wavelength can be determined by looking at the different spectrums. Okay, radio waves have the longest wavelength. Their wavelengths can reach lengths of up to 20 meters. That's really, really long. Okay, because they have such long wavelengths, they can travel great distances, and they're great for communication. Microwaves are a little bit shorter. Their wavelengths range from a few centimeters to maybe a few millimeters. They're much shorter. Microwaves are good at transporting energy, and they're great for heating food. Microwaves specifically react with water, so H2O. And do you guys know that grating on the front of your microwave oven, and there's all those little holes there? Those holes are all smaller than the wavelength of a microwave, and that keeps it from hitting your face and making your face heat up. Because remember, the human body is about 80% water. Infrared waves can usually represent heat. Heat is usually seen in the infrared spectrum. So if you ever have one of those thermometers that you just click and point at something, that is reading the infrared spectrum. Heat comes off as infrared radiation. UV light is a bit shorter than infrared, and now we're starting to get to the shorter wavelength, higher energy. So this is a shorter wavelength. We'll put it right there so we can have an indicator in the middle. So it's a shorter lambda, it's smaller, but it's got some more energy than infrared. Some more big E, okay, more energy. UV light can actually harm your skin, and it can cause sunburn. Okay, it's important to wear sunscreen. UV light comes straight from the sun. X-rays are used for bone scanning. Medical professionals use these all the time so that they can see what's inside your body. I'm having trouble spelling today, but that's bone scanning. That's what that means right there, bone scanning. Okay, and it's important that you wear the lead vest when you get an X-ray, because those X-rays have higher energy, and they can actually be damaging. They can damage you if you don't have the proper protection. That's why you wear the lead vest inside the doctor's office when you get an X-ray. It protects your vital organs from those X-rays. Gamma rays at the bottom have the highest energy. They have the highest energy, and they have the shortest wavelength. Gamma rays don't occur very often. In order to generate a gamma ray, you have to have lots of energy. This energy is usually in the terajoules, which is 10 to the 12 joules of energy for a single particle. So that's a lot of energy. And that a lot of times comes out of a radioactive decay of some unstable piece of matter, or it can come out of a particle collision at high energies, like at the CERN particle accelerator in Europe. The one spectrum of light we haven't talked about yet is visible light. Visible light ranges from about the 400 nanometer range to the 750 nanometer range. Visible light consists of the colors of the rainbow, so red, orange, yellow, green, indigo, blue, and violet, Roy-G-Biv, just like the colors of the rainbow. Okay, and the wavelengths match up like this. Red is in the 750 nanometer range, just under, and violet is way down here at about 400. This is a very small range of wavelengths here. It's a very small range of wavelengths. The reason in this, so this means that we can only see a very small amount of light. However, there's still lots of cool things that light can do. Light brings forth a lot of different, very beautiful colors. Okay, just look at the rainbow outside of a rainstorm. There's all those beautiful colors, and they combine together. However, they are divided into two categories: additive and subtractive. For additive, you need to think about TVs. You need to think about your iPhone screen or your iPod screen. Okay? These all rely on additive color combinations. On the opposite side of the spectrum, we have subtractive. Think paint. Okay? Think the color of objects. Okay? There's a big difference here. In additive, we have two lights coming together. So it's like I could take two flashlights here. Right? They could shine some light. And they'd be different colors of light. And that would form a new color here. Because they're adding together. They're combining to make a new light. On the opposite side of the spectrum, over here with the subtractive, it's a little bit different. You're taking one color pigment, you're taking another color pigment, and when you mix them together, the only color that shows is the one in common. Okay, so the only color that shows is the one that's in common. Okay, this is the one that's in common. Here, with the subtractive, it's like a mixture of the two, so it's everything that's there. Okay, so it's all added together. So that's the big difference between these two. Now we know the difference between additive and subtractive, we need to think about the primary colors of each. For additive, the primary colors are red, green, and blue. Those are the primary additive colors. For subtractive, it's a little bit different. We've got cyan, yellow, and magenta. Those are our primary subtractive colors. So for example, let's say you're in the art classroom and you want to have the least amount of colors, but you want to be able to make the most amount of colors by mixing them. You would need these three colors plus white. Alright, because if you combine all three of those colors together, you'll get black. If you combine cyan and yellow together, you'll get green. Because that's what's in common between those two. If you take magenta, and let's see, is it yellow? Yeah. You take magenta and yellow, you'll get blue. And finally, if you take cyan and magenta, you get blue. Okay? That's how those are related. We could also look at it in the opposite direction. If we took a look at the opposite direction, let's start combining additive colors. So if we put red and green together, we're going to get yellow. If we take red and blue together, we're going to get magenta. And finally, if we take green and blue, we get cyan. Okay? So these colors are related. They're related in a little bit. Okay? And you can see the relationship there. You can scroll back a little bit on the video and you can see the opposite relation if we miss with our subtractive colors, get the red, green, and blue. Okay? So your TV can get any colors that your paints can get. You just need to start at a different spot.